In the last couple sections we were looking at volume, which is kind of like the three-dimensional XYZ axis. Now we're going to be looking at lengths of curves or arc length. So this is two-dimensional. This is looking at the XY plane and looking at the length of a curve. Now if we think about taking a piece of string and covering the length of the curve and then straightening it out and then measuring it with a ruler, that would be arc length. Now let's go ahead and look at a specific example where we're looking at the arc length of a line. And again, when you say arc length of a line, it's just the distance between 2 points of a line. But I want to show you how the formula works. So this is a line with y-intercept of 2 and a slope of 4. Okay, and then of course we're going to go from 0 to 4. So our other point on the curve would be 4 times 4 is 16, plus 2 we'll say is right here at 18. So this is the ordered pair 4, 18, and then at 0, of course, we're right here at 0, 2. So I'm trying to find the distance between these 2 points going through here. Now that's a straight line. It might not look like it, but it is. Let me see if I can make it a little better. That's a little better. So I'm trying to find the distance between these 2 points on the curve. So again, we have a nice formula called the distance formula that helps us do that. So let's go ahead and use the distance formula first. Now the only time I can use the distance formula is if I'm looking at a line. If I'm looking at any other shape or any other curve, I can't do that. So if you'll recall, the distance formula is equal to the change in the x's squared plus the change in the y squared. Square root of all that. So again, we're using our ordered pairs. So the change in the x's would be 4 minus 0 quantity squared. So again, I'm using 4 from here minus 0, and then 18 minus 2 would be the difference in the y values, quantity squared. 4 minus 0 is 4 squared, 18 minus 2 is 16 squared. So as I'm simplifying, 4 squared is 16. 16 squared is 256. I add these together and I get the square root of 272. And then of course we want to simplify this. 4 goes into 272. I believe 16 will as well. So this simplifies to root 16, root 17, 256 plus 16. So this simplifies to 4 root 17. And this would just be units. So if our units were length, would be like feet, inches, meters, something like that. So this is using the distance formula that we've used forever. Now what we want to do is learn a new formula. And again, this is the one for arc length. And of course, length of curves is another way that we could call this. So the formula for arc length is L equals the integral from a to b. Now usually we're working with dx's, but in your homework set you have one that you're working with dy's. So you just have to look at the formula that's given, and we're integrating from wherever we're starting to stopping, your endpoints. And then it's the square root of 1 plus the derivative f prime of x quantity squared dx. Now if we're going the arc length, then we're using our y values because everything is solved for in terms of y. This would go from c to d, square root of 1 plus f prime of y squared dy. So these are definitely the formulas that you'll want to know for this section. So using the same exact example that I have up above, let's go ahead and see if we can match the arc length with that distance formula. So from above, we know that we're using y equal 4x plus 2. And we're using this over the interval 0 to 4. Now if you look at this formula, the important thing that we need to find here is the derivative. So y prime is equal to 4. It's a prime mark. So now I can plug that in to my length formula. Length is the integral from 0 to 4 in this case. Square root of 1 plus the derivative, which is 4 squared dx. So simplifying, 4 squared is 16. 16 plus 1 is 17. And the integral of root 17 is going to be root 17x. The x is not under the integrand, evaluated from 0 to 4. So I'd have root 17, and then I'd plug in my 4 minus 0, my upper minus lower, and you can see here I get 4 root 17 for my arc length. So you can see we get the same solution either way. The distance formula only works with lines. The arc length formula works with anything. Now some of these integrals can get pretty ugly. Things are easy to take the derivative of, but they're more difficult to integrate. So make sure when you're working with these you look at the instructions carefully. With the instructions, what happens is they'll say something like approximate the curve. And if they say approximate the curve, basically what they mean is make sure you look at using your calculator, trying to come up with a value with your calculator, because it's not integratable using the techniques that we know so far. So one example that this could be similar to would be to find the arc length of the curve. Let's use y equal cosine of 2x on the interval from 0 to pi. So sometimes it's nice to graph these and then look at the graph so you can kind of get an idea of what you're looking at the arc length with. So let's go ahead and look at the arc length of cosine of 2x between 0 and pi. Now most of these we won't have a curve sketch for because they're so complicated, but this one's a pretty straightforward one to look at a curve sketch. So we know the general shape of the cosine of 2x is something like this. This 2x takes the old period of the cosine curve, which was 2 pi, and I divide it by 2, and it squeezes in the entire cosine graph in a period of pi. So let's go ahead and have a look, and again we're going to focus in on 0 to pi. So the cosine curve, if I plug in a 0, the cosine of 0 is 1, so I'm up here at 1. And then I know it's going to go through a full period between 0 and pi. So we chop up our quadrants here, are going to be a little bit different because I have that period change, and I know I'm going to start and end up here. So let's go ahead and plug in pi over 2. 2 times pi over 2, 2's would cancel. The cosine of pi is 0, so it's going to cross here, and I think my graph is going to end up coming down and then up, and then we'll see that turn back up again as well. So let's plug in our pi over 4 to see what's going on. So pi over 4, 2 goes into 4 twice, so the cosine of pi over 2 is, whoops, I put my point in the wrong spot. It's going to cross here and here. If I plug in pi over 2, the 2's cancel and the cosine of pi is -1. So here's my graph. So basically I'm looking for the length of this line. So if we took a piece of string and overlaid it, we could just copy that curve and then stretch it out straight and measure it on a ruler. We'd have the same distance, but we don't have that luxury to do that. So we want to use our formula for the arc length. So the arc length is going to be equal to 0 to pi square root of 1 plus the derivative squared. Okay, so we need to figure out what the derivative is and then we'll square it. Now everything is in terms of x here, so I have dx's. So if y is equal to the cosine of 2x, y prime or dy dx or f prime of x is going to be equal to the derivative of the cosine is negative sine of 2x times the derivative of 2x, which is 2. So this is negative 2 sine of 2x. Now again, if you look on your directions, sometimes it'll say approximate and sometimes it will say exact. Because we don't have the integration techniques for some of these, what's going to happen is you read that carefully because you will not be able to integrate all of these by hand. If it says to use an exact solution, that means you have the skills to integrate it. If it says to use an approximation or to use technology, then by all means you should do that. Now on a test, whatever I give you, I'll either ask you just to specifically set it up or integrate it. And if I ask you to integrate it, it will definitely be a technique that you would know. For this one, we are going to approximate the curve because we do not have any techniques that will help us integrate this right now. We will soon in the next unit or so, but for now we don't know how to integrate this. So if we go through and we use technology to approximate our solution here, you could use something like Wolfram Alpha, Mathway, your calculator. If you guys are using Maple, you can use that as well. And when we do this, we get an approximation of 5.270. So again, if they say exact, that means you should be able to integrate it by hand. And of course you'd want to show all of your work, especially on your handwritten homework. And then you can always double check using some other technology, but you need to show all of your work. So this is an example of where we'd use some technology to find our solution. Now I'm going to look at our next problem, and with our next problem we should be able to integrate this one by hand, and I will take the time to go through and show you the integration technique. It's just algebra preparation basically, but it can get a little bit tricky, so we'll make sure that we focus on some of the techniques here. So for this equation we're asked to find the arc length, and I wouldn't expect a curve sketch here, of x equal, now we're used to y equal, so we're using dy's here. And again, I don't expect you to know this shape. If you want to go through and graph it, you can, but we really don't need to see the graph. It's just interesting sometimes. So we want to find the arc length of this curve between 1 and 5. So to get started, definitely not the distance formula. This is definitely a nice curve here. It's not a straight line. So I need to find the derivative, because remember the formula that we're using is the integral from 1 to 5 square root of 1 plus f prime of y, and I know it's in terms of y because this right hand side is squared dy. So on a lot of these it's easier if we look at this and we focus in on the integrand, the radicand in the integrand, so this underneath the square root sign. So if we know what x is, we should be able to rewrite x. So we have y to the 4th over 4 plus 1/8 y to the negative 2. So I'm going to flip that up top. Now we're going to take a derivative, so that would be dx dy. I bring the 4 down, decrease the exponent by 1. Okay, same thing over here. I'd bring the negative 2 down, decrease the exponent by 1, and this is my derivative. But I want to simplify this quite a bit. So I'd have dx dy equals, the 4's cancel, y cubed. 1/8 times a negative 2 is a negative 2/8, which is a negative 1/4. And then the y to the negative 3 flips down into the denominator. And then I find a common denominator here. And again, I'm trying to simplify this to get it into a form that I can plug in here. So finding a common denominator, I'd multiply both top and bottom by 4y cubed. So I would be left with, it looks like 4y to the 6th minus 1 all over 4y cubed. Okay, so that's my simplification of my derivative. Now if you notice in this formula, I need the derivative squared. So let's go ahead and look at dx dy squared. So that would look like 4y to the 6th minus 1 quantity squared over 4y cubed quantity squared. Now when this says to square this binomial, I cannot take the 2 and distribute it. I need to FOIL it out. So it's going to look like 4y to the 6th minus 1 times 4y to the 6th minus 1. And of course 4y cubed squared would be 4 squared is 16, y cubed squared would be y to the 6th. Now I haven't plugged anything into my formula yet. I'm just trying to simplify. So this is dx dy quantity squared. So 4 times 4 is 16y to the 12th. Minus 8y to the 6th plus 1 all over 16y to the 6th. So this is the part that goes in for f prime of y quantity squared into my formula. Okay, so let's go ahead and have a look at that formula again. Arc length is going to be the integral. This one was from 1 to 5 of the square root of 1 plus. Now all of this is under the radical. 16y to the 12th minus 8y to the 6th plus 1 all over 16y to the 6th. The 16y to the 6th is not down here, it's underneath the radical. And it's really important that you notice that, because that's the only thing that makes this integratable. So we'd go through and find a common denominator. So I'd have 16y to the 6th plus 16y to the 12th minus 8y to the 6th plus 1 all over 16y to the 6th dy. Now of course all of this is still underneath the square root sign. Now if you're wondering where this 16y to the 6th came in, I just multiplied top and bottom by 16y to the 6th here. As we continue to simplify, we're trying to get this into a form that I can integrate. Now the square root of 16y to the 6th, that's doable. That would be 4y cubed. Now up here when I combine like terms, 16y to the 6th minus 8y to the 6th is 8y to the 6th. My highest power though is 16y to the 12th plus 8y to the 6th plus 1 dy. It's still not in a form we can integrate it, but I do notice that 16y to the 12th plus 8y to the 6th plus 1 is simplifiable, if that's a word. This would be 4y to the 6th plus 1 and 4y to the 6th plus 1. So if you look at factoring that, kind of like a reverse FOIL, that would work perfect. Integral from 1 to 5, square root 4y to the 6th plus 1 quantity squared over 4y cubed dy. Now the square root of the something squared here is just this base back. So this will be the integral from 1 to 5 of 4y to the 6th plus 1 over 4y cubed. Now we still can't quite integrate this. We're getting closer though. So our technique that we're going to use here is to separate the numerator. You can always separate the numerator. You can never separate the denominator. And this is one of the reasons why it's so important to be able to show your work when you're integrating, because there's a lot going on here. We can't just skip to a solution. Now as we continue to rewrite, 4y to the 6th over 4y cubed, the 4's cancel. Y to the 6th over y to the cubed is just y to the 3rd, or y cubed. Now this one, the y cubed pops up top, but the 4 stays down below. And now I'm finally ready to integrate this. So we had to do a lot of this prep work to get it into a form where we could integrate it. And now I can just use the good old power rule. So we'll add 1, divide by the sum. Okay, we'll add 1 and then divide by the negative 2. So I get y to the 4th over 4. And then I have a minus 1 over 8y squared. Now I can evaluate this from 1 to 5. So the 1/4 I multiplied by the negative 2 in the denominator. That stays in the denominator, and the y to the negative 2 flips. So let's go ahead and plug in the 5 first. It'd be 5 to the 4th over 4 minus 1 over 8 5 squared. So that's my upper. Make sure you use parentheses with that lower. 1 to the 4th over 4 minus 1 over 8 times 1 squared. So 5 to the 4th is 5 squared is 25 times 25 is 625 over 4 minus 5 squared is 25 times 8 is 1 over 200. And I'll go ahead and distribute this negative right now. So that'd be a negative 1/4 plus 1/8. So we need to simplify this to get to our solution. So 1 right there. So as we're working through this, I can drop my brackets, and I'm going to kind of group my common denominators together. So I have 625 over 4 minus 1/4 is going to give me 624 over 4 plus an 1/8 minus 1 over 200. I want to find a common denominator here. I know I could reduce this, but I'm going to go ahead and find a common denominator. So if you want to reduce it, you absolutely could. We're going to get the same answer in the end. So we'd end up with 1248 over 8 plus 1/8 minus 1 over 200. 1248 over 8 plus 1/8 would be 1249 over 8 minus 1 over 200. We need to find the common denominator, so I'm going to multiply top and bottom by 25. So 1249 times 25, that's going to be, it's going to end in a 5, 31,225 over 200 minus 1 over 200, 31,224 over 200 is our answer, but it's not the final answer because I can reduce this. So again, we're working with 31,224 over 200, and then I'm not sure exactly what the highest number we can divide this by. I know they're both divisible by 4 because the last two digits are divisible by 4. So I'm going to divide top and bottom by 4. and I end up with 47806 over 200 divided by 4 is 50. And both of these are even, so I can divide these by 2. And again, if you caught that they were divisible by 8 right away, that's great. And half of 7,000 is 3,500. Half of 800 is 4, so that's 3,903 over 20, or 50 divided by 2 is 25. So that's the arc length, and that's an exact answer. It's not an approximation. You can definitely check this using your calculator, Maple, Mathway, Wolfram Alpha. It doesn't matter which one you use, but you have to be able to do these by hand, and you have to be able to show your work with the integration. You can clearly see here this one is not doable just to estimate it or guess at the integrand when you're done. So using the idea of antiderivatives doesn't really work well here because the antiderivative isn't very obvious. Now this is one of the tougher ones that you'll work through. Several of the problems are just like this. So again, simplifying is the key. Looking for that perfect square and factoring up here is going to be important. So again, looking for this process right up here and factoring into a perfect square, and then taking the square root of that perfect square and then separating the numerator is going to be the kind of the key that we use here to solve these. These are fun problems. There are long problems, as you can see, but definitely doable if you stick with them. Make sure you verify and check your work, but make sure you show all of your work, especially on the handwritten homework if you would like credit. As usual, if you have any questions, please text me. You can also email me. You can also use Pearson Connect. And if you want to stop by my office if you're on the Spearfish campus, that's great as well. Or if you want to meet for online office hours, let me know and we'll set up a time that works for both of us. As usual, good luck.